Now going to look at exponential models, story problems involving exponentials. And the first one that we're going to look at is a banking problem. From experience, the manager of a bank knows that between the hours of 3 p.m. and 5 p.m., people arrive at the rate of 15 people per hour, or about 0.25 people per minute. The following formula from statistics is used to determine the likelihood that a person will arrive within t minutes of 3 p.m. So here's our function, and notice that this 0.25 people per minute shows up right here as a negative on our e. And so if we plug in a t value, 10 minutes say, we get the likelihood of somebody showing up. And so in its exact form, we have 1 minus e to the minus 2.5. But we want to know what that is in decimal, so we're just going to grab our calculator, and we're going to type this into our calculator. And so we're going to do 1 minus 2.5 negative, and I'm going to hit this inverse button and e to the x, and hit equals. And I'm going to get 0.9179, around to 4 decimal places, 0.9179, or 91.79% chance that someone will arrive in the first 10 minutes that we're open from 3 o'clock. And so I can use that to schedule people and to afford breaks if I know that I've got enough people to handle there being a person in the first 10 minutes. What about the chances that someone will show up in the first 25? So again, B, we're going to plug in 25 instead. And so that's going to be 1 minus e to the minus 6.25, which we go back to our calculator, and we do 1 minus, and remember we're going to put the number in first on this calculator, change its sign to our e to the x and hit equals, because there's a 99.81% chance, 0.9981, or 99.81% chance that a person will arrive in the first 25 minutes after 3 o'clock. And so this is one model that we can use that's very useful and can help a manager know how to schedule and how to afford breaks to their employees. The next type of model that we're going to look at is a half-life model. So suppose that I have the following information. This is much bigger, so we're going to reshape it, put it down. And so we've got the half-life of thorium-227 is 18.72 days. So in 18.72 days, the sample that we have shrinks by exactly a half. And every 18.72 days, that example shrinks by another half. So suppose the researcher possesses a 10-gram sample of thorium-227. The amount A in grams of thorium-227 after T days is given by, so notice we're giving you the model, A of T equals 10 times 1/2 to the T over 18.72. So what we want to know now is how much is left after 10 days. So we take our A of T, and that's going to be equal to 10 times 1/2 raised to the 10 over 18.72. And so we grab our calculator, 10 times 0.5 raised to the parenthesis 10 divided by 18.72, close parenthesis. Notice we can see the whole thing here, so when I hit equals, I can see that I'm going to get 6.905 grams left. 6.905 grams. If I let it sit for 18.72, this is easy. I can do this one without the calculator, because 18.72 over 18.72 reduces to 1. 1/2 to the 1 is 1/2. 10 times 1/2 is 5 grams. We cut exactly in half because we let it sit for the full half-life. For C, so this was A and that should be a 10, B, and C, we want to know A of 74.88, so we plug this in. 18.72, and this is going to come out at 10 times 0.5 raised to the parenthesis 74.88 divided by 18.72, close parentheses, equals, we're down to 0.625 grams. And our last one is 100, and we can do the same thing, and I'm just going to jump straight to the calculator. We're going to do 10 times 0.5, because that's the same as a half, raised to the 100 divided by 18.72, close parentheses, equals, and we have less than 1/4 of a gram after 100 days. So that was 0.247 grams. And so the longer we let it sit, the more of it disappears. And so this is using our exponential model in a calculator to successfully evaluate exponential models.